would be measured as a ratio of load bearing capacity to weight. However, there were a number of constraints and considerations, such as using only number 3 spaghetti, using only superglue as an adhesive, a minimum length of a 350mm span and 80mm width, and a maximum bridge weight of 200 grams. There were no restrictions for the design of our bridge, so the rest was up to our creativity. Having considered the requirements of the spaghetti bridge, our group decided on building a truss bridge design. A truss bridge was suitable for our bridge construction, as the bridge only had to span a small distance of 350mm. In addition, trusses provide an optimal strength to weight ratio and were easy to produce using spaghetti and superglue. Due to the brittle nature of the spaghetti members, it was ideal to keep the compression members as short as possible. This led to consideration of both the Warren and Pratt truss designs. We selected the Warren truss design and added a king posts for extra support. Furthermore, we chose a triangular cross-section for our bridge as opposed to a square cross-section, which would provide extra support and reduce racking under load. The triangular cross-section would allow us to reduce the weight of our bridge, as there is only one single top chord. We considered 3 angles for our trusses, 30 degrees, 45 degrees and 60 degrees. With a reactive upwards force at point A of 98 newtons or 10 kilograms, we were able to calculate the compressive force along the members. We selected the angle for our trusses to be 45 degrees as it was a compromise of reducing compressive forces while maintaining a shorter length. Although selecting a steeper angle such as 60 degrees would reduce our compressive forces, this would make the bridge taller and therefore increasing the weight of the bridge. Through research, software and our own calculations, we were able to identify the tension and compression members in our truss layout. This was achieved by applying a nominated downwards force, which would represent the force on the testing machine. We then produced a free body diagram and followed the process to calculate the tension and compression of each member. Using the suggested online software Truss Solver, we were able to verify our calculations. The issue regarding the length of the bottom chord arose, as the average length of spaghetti was around 260mm. Therefore, we needed to connect spaghetti in a way to produce a strong joint, which would span the 400mm. Our solution to this issue was to produce 2 bundles of spaghetti. Through counting the number of strands in one bundle, we were able to determine the amount of strands which should be present in the centre of the member. We then snapped an equal number of strands of spaghetti from each bundle so that the bundles merging would produce a 400mm long bottom chord. This meant that the sum of the intersecting strands in the centre would equal the number of strands in either bundle. This would provide a consistent diameter throughout the entire bottom chord. However, we did recognise that this would produce weak points at the starts of the joints. Using the provided tensile strength information, we were able to calculate an approximate maximum load for our tensile members. By finding the ratio of our tensile members to the singular strand of spaghetti, which was given as 2mm, we were able to find the tensile capacities for the tensile members. However, in practice this is not the case, as the members are not one uniform piece of spaghetti, but rather an arrangement of multiple strands of spaghetti. The joints identified in the bottom chord can be likened to that of a knot in timber. As determined in our UniSA Mawson Lakes site visit, knots in timber are often the failure point. Therefore, it significantly reduces the accuracy of a predicted failure load. The construction process was as followed. Step 1. Weigh the bundle of spaghetti per individual member requirements. Step 2. Apply rubber bands to constrict the bundle. Step 3. Apply adequate superglue, including the internal structure, and wrap with baking paper to provide compression to the circumference of the spaghetti member. Step 4. Cut to required length, leaving some excess for assembly and measuring defects. Step 5. File and sand to the appropriate joint angles. Upon its completion, we then tested our first bridge. After analysing our broken bridge, we found that the bottom chord broke where the joins were, thus this was a weak point. Following this, we decided that the bottom chord was our main issue with our bridge design, and that we could use the remaining weight in our 200 gram quota to strengthen the bottom chord and provide a stronger bridge. We produced an additional concept for our bottom chord, which staggered thick members of spaghetti in a core surrounded by a shell of spaghetti. The aim of this design was to provide no specific weak point along the length of the bottom chord. Following our bottom chord adjustment testing, we found that the difference between the two designs was almost negligible. Hence, we used the original design, which was easier to produce, and thickened the members so the bottom chord weight was double. We also reduced the amount of cross bracing members on the bottom of our bridge and reduced their thickness in order to reduce the bridge's weight. Upon testing our second bridge, the bracing snapped at a weight of approximately 12.5 kilograms, and therefore we were allowed to retest. In our second attempt, the bridge managed to hold a load of 17 kilograms. However, with the removal of one of the bracing members, the load was not directly applied in the centre. This was a strong improvement from our first bridge. However, creating a stronger joint would prove more beneficial in the future.